Hello, and welcome to the UC Riverside Unmanned Aerial Systems Flight Readiness Review. In this video, we will present a brief overview of the various systems on our aircraft, the mission tasks we plan to complete, and an analysis of expected performance at competition. Our 2017 development team was comprised of over 30 students from both the mechanical and electrical engineering departments, with support from IEEE and the Center for Environmental Research and Technology. My name is Igor Krasowicz, and I am the project coordinator of UCR UAS for the 2017 competition year. I am a fourth-year computer engineering student with 1 year of competition experience. I have relevant experience in robotics and computer graphics. I will serve as team captain at the competition. My job is to make sure that everyone performs their jobs as safely and effectively as possible.
Hi, my name is Calvin Ta, and I am a second-year computer science major, and I am the ADLC team lead. And this is my second year in the competition. My role on the ground will be to manage the ADLC tasks of the UAV.
Hi, I'm Wee Tran. I'm a first-year computer engineering student. This is my first year on UCR UAS. I have come from a small background of robotics and amateur radio, and I am on the flight team as a ground support. Some of my duties on the flight line include safety, airframe maintenance, and troubleshooting, so that the pilot can concentrate on the mission.
My name is Evan Scott. I'm a second-year electrical engineering major and the safety pilot. I have flown radio-controlled airplanes since the age of 13 and have been designing and building my own UAVs for the past 4 years.
My name is Omar Praza. I am a second-year computer science major. On ADLC, I am doing the pipeline and experience in OpenCV. And for the competition, I am in charge of planning the mission control and flight plan.
This year, we decided to use system components that would increase speed, stability, and accuracy, using a mature architecture and codebase from previous years. To this end, we chose the NVIDIA Jetson TX1 as our onboard computer. We will use the parallelism of this mobile-grade GPU to accelerate vision tasks. Our main payload camera is the Olympus Air, a 20-megapixel lens-style camera. Its small size and open-source software make it easy to integrate with our payload. Our experimental secondary camera is a machine vision unit modified to operate in the near-infrared. This will increase the accuracy of object detection using multispectral data. Dual FPV cameras offer real-time feedback from the vehicle. Our payload features one short-range onboard Wi-Fi network and, as with last year, a high-powered 2.4 GHz data link with the ground station.
Hello, my name is Benjamin Geen, and I am the current mechanical coordinator for UCR UAS for the 2016-2017 school year. Unfortunately, I will not be able to make it to the competition this year, but I want to talk a little bit about the development process of our UAV, which is the Finwing Sabre. The Finwing Sabre is an RC kit of a high-wing all-foam pusher. So the reason we chose the Finwing Sabre is because it's created out of all foam. That makes it lightweight, and because it has an expanded payload bay, this allows for more battery space, which would allow for extended flight time and also carries over in having a better endurance. The Finwing Sabre is also great for flat mapping and aerial photography due to its spacious interior. It has a camera bay for both the fuselage and within the nose as well. So due to such of a low cost of the fuselage, it's easy for us to buy new RC kits and just use them whenever it's readily available. The optional landing gear on the fuselage is one of the best attributes of the fuselage due to the fact that it's able to be thrown for takeoff, or it can have a wheel mount attached to it.
Hi, I'm Lucas Glass, and I was a mechanical lead for this year's team. The main task I was in charge of for this year's competition was the air delivery. The design for the casing around the water bottle underwent many different design tests. For these tests, we dropped it from about 60 feet high, and this would explode a normal water bottle without any case around it. We tried out 3D printing the case, but that would have required us to reprint the design after each drop since it didn't survive. We ended up deciding that a combination of plastic and styrofoam would be good for the casing. All of our tests resulted in the water keeping all of its water. We have performed a successful 300-foot drop from the plane, and the trajectory of the payload for that test did match what my MATLAB program had estimated. Overall, on our initial test, we did score a 60% for the air delivery task.
We plan to attempt the mission tasks with the following confidences. Autonomous flight, high. Waypoint capture, high. Waypoint accuracy, high. Our mature autopilot system from previous years allows us to safely and reliably operate the autonomous portion. Stationary obstacles, medium. Moving obstacles, low. Obstacle avoidance was briefly tested on stationary obstacles using last year's approach. Search area, high. Off-axis target, low. Geolocation, medium. We believe that our airdrop design will allow us to safely and precisely deliver our payload to the target area. We took an incremental approach to systems testing this year. A major milestone was to achieve full payload integration and testing on the ground, which allowed for hundreds of development hours before being installed on the airframe. Each component of our ADLC pipeline was individually tested and benchmarked. Test data consisted of images from previous competitions, as well as test photos taken using current hardware. We performed 18 flights on the competition airframe. This does not include flights made on backup airframes or previous year's airframes, which were used to train ground personnel. 7 of these flights were full manual, and 11 included autonomous flight. We predict a maximum flight time of 40 minutes. Through our flight tests, the autopilot achieved waypoint miss rate of around 15%, partly due to the high winds in our test area. This, however, boosted our team's preparedness for unfavorable conditions.